Let me stand in front here and everyone knows what I look like. So I want to say welcome everybody who's joining us virtually and those that are here in person. Thank you for, braving the weather or deciding to stay home and catch this important information from home, the comfort of your home. Tonight's talk is very important. I tried to plan these winter lecture series around, at least to have one around current events that occurred this year that impacted our natural resources. And we can all remember the smoke from the wildfires up in Canada this year, and I wanted to have a talk from an expert in the field. And this is where we reached out to Dr. Hansen from the Carey Institute, which leads us to our speaker tonight. So tonight we have Dr. Winslow Hansen. He is assistant scientist at the Carey Institute of Ecosystem Studies and also the director of the Western Fire and Forest Resilience Collaborative, which is an ambitious multi-year initiative with 10 research teams across the United States, co-developed with decision makers. He is also affiliate faculty with ecology, evolution, and environmental biology at Columbia University and the International Arctic Research Center at the University of Alaska Fairbanks. His research is focused on advancing knowledge of the changing Earth system by uncovering rules that govern interactions and feedbacks among forest disturbances and climate. So please join me in welcoming Dr. Hansen.
Thanks so much, Matt, for the wonderful introduction. It was really a thrill to get the invitation to speak in this lecture series today. Is the volume okay? Can everybody hear me all right out there? And
Oh, 1 second. Right here.
how's that?
That's good for the volume.
Great. Okay. I was just saying thank you so much for the invitation to present to you today. I was really thrilled. And I'm very sorry I can't be there in person. I've been looking forward to this for months, so a little disappointed to not be with you in the room, but snowpocalypse is coming and it seems prudent to not try to drive home an hour back to Millbrook. So there's a couple reasons why I was really excited to come here. The first is that about a year ago, I met Starling Childs, and he regaled me with stories about his time up in Alaska. And while I'm not going to talk about Alaska today, it's a really special place for me. My wife and I spent 7 years living up there, and we still do a lot of research up there in the summers. And then secondly, I work very closely with a scientist here at Carey who just retired a year or so ago, Charlie Canham, who spent most of his career doing some of the most high impact work at Great Mountain Forest. So it's kind of a mythic place in my mind, and I'm really excited to hopefully get out there and see it this spring. So I'm a scientist at the Carey Institute of Ecosystem Studies. For those of you who are unfamiliar with it, it's a nonprofit ecological research center in Millbrook, New York, about an hour away from you all. And we focus on trying to understand how our ecosystems are changing and why. My lab in particular focuses on thinking about how forests of particularly Western North America are likely to change over the next century with increase in climate change and disturbances, especially fire. And that's what I'll be talking with you about today. So here on this very title slide, we're actually looking at a picture of Yellowstone National Park, a place where I did my PhD research. This was a fire that burnt in 2016, and you can see it was high severity and stand replacing. In fact, some of the trees that were standing before the fire have been completely consumed, and all that's left are the pencil stubs there. So really, quite an impactful disturbance and increasing in prevalence. But it's important to note, it's important to note that fires is a natural thing in Western North America. They've burned for something like 350 million years. And high severity fire is something that many of the tree species are adapted to. So here we're looking at a picture of forests in Western Washington, west of the Cascade Crest. These are highly productive, very wet Douglas fir forests, not a place that you think of having fire. But it turns out that even these forests historically burned on the order of hundreds to thousands of years. And when they did burn, they burn in these tremendously large stand replacing high severity fire. So even in some of the wettest places in our country, fire was a critical thing. But we also know if you don't have your head in the sand and you consume any media at all, that fire is becoming quite a prevalent part of life, particularly in the Western United States. So this is a picture from downtown Ventura, California, as the Thomas fire that burned in 2017 came right up to the edge of town. Santa Barbara also had this fire come very close. And so this is an occurrence that's increasing. And in fact, with climate change, people have suggested that we're actually entering a new era called the large fire era, or if you're on the dramatic side, the large fire crisis. And for me, fire in Western North America is a lived experience. It's deeply personal, and it's why I do the research I do. I grew up in Bozeman, Montana. You can see the star there on the map, roughly where we're located. And I spent, the first 22 years of my life living in the Rocky Mountains, and then went up to Alaska as a master's student, which also experiences quite large fires. And in fact, when I was a kid, I think I was like 8 or something like that, a fire burned right through our neighborhood. This is a picture of that fire. Our house is right here. We were evacuated and spent a week in a hotel. And I thought it was just tremendous fun. I got to spend a week in a hotel with my friends and go hang out every day. Didn't really understand the implications of it, but our home survived because firefighters came and covered the entire thing in foam that kept the flames from consuming it. And then the next year, I remember going out into those very woods that were, burned, and finding mushrooms popping up and little tree seedlings all over the place. So I think that experience planted in me this kind of interest that I've pursued ever since. Now, despite the doom and gloom story that often accompanies the large fire crisis, I wanted to just start off by saying I think there's actually many reasons to be really optimistic about our ability to live sustainably with fire. There's a couple reasons for that. Even in just the last 5 years, we've seen tremendous investment from federal government, state government, and even philanthropy getting in the game to think about what are the strategies that might help us deal with this new reality. So just as one example, the federal government, so Congress, Senate, included something like $24 billion for wildfire preparedness in the Inflation Reductions Acts and Infrastructure Investment and Job Acts, of which 10 billion went to proactive forest management. So these are strategies that help us reduce fuel loads, which we're going to talk about later in this talk, preparing our forests to not burn so severely when fire does get in there. There was also funding to improve suppression responses, safety for firefighters, infrastructure, resources for that, and then community adaptation. So money to help communities adapt in terms of home hardening and making it so that when fires do come into neighborhoods, they're not so catastrophic. But despite that investment, we still have tremendous scientific uncertainty in a lot of dimensions that constrains our ability to make these critical decisions about how to manage fire and how to live with fire on our landscapes and what the implications are going to be. So a couple of them is, first, we have a lot of uncertainty in the strategies that are used to manage fire and forests. So here we're watching a video of a Forest Service employee using a drip torch to start a prescribed burn. You'll see just the surface fuels are being burned, and that reduces those fuel loads so that if a wildfire comes into this space in the next few years, it's not going to burn quite as catastrophic and hot and severe. Now, we really know that these are effective at the stand scale. And what I mean by that is as the fire comes up to this place that's been treated, we know these treatments are going to change fire behavior. But we have no idea how those treatments scale. So we don't know how much forest we need to treat and in what configuration and in over what intervals to have landscape to regional or even continental effects on wildfire. Because climate change is occurring so rapidly, and because fire is so responsive to climate change, as we're going to talk about more in a little bit, we also have a lot of uncertainty about what our forests, what fire regimes are going to look like in just coming decades. So even as soon as 2040, 2050, our understanding of what these ecosystems in the West will look like is super unclear. So with that uncertainty in mind, I wanted to spend the rest of the talk kind of doing something, I don't know, a little fun. So we're going to spend the rest of the time addressing 12 common questions about fires and forest resilience. And this is meant to summarize what we know so far and where the uncertainty lies and what we can do about it. The first question, of course, being here in the Northeast that I've been getting pretty much constantly since this summer is what the heck is going on with all the smoke from the Canadian fires? So let's start right there. Well, it turns out that 2023 was a record-shattering year for fire in Canada. Unlike most of the United States, Canada experienced really unusually warm and dry conditions that dried out the fuels and caused massive burns. It was something like 12 times more area burned this year than the 10-year average. And something like 45 million acres in the end were consumed. So I spent the entire summer watching the map, as any good fire ecologist does. And there were times where it looked like just the entire country of Canada was on fire. Turns out, this is about the area of Florida if you were to lay those burns over it. So quite a large area. And the most important thing, in terms of widespread impacts from these fires that affects us here in the Northeast is smoke. So smoke is far flung from fires. It travels in directions that are largely driven by atmospheric dynamics, so they can be hard to predict and inconsistent where that smoke is going to end up. Smoke from the Canadian fires was traveled as far south as Dallas, Texas at certain points during the summer. So much of the United States, not just the Northeast, experienced those conditions. And in terms of impacts on people, besides the acute impacts of homes being burned, people being injured and killed, smoke is kind of the major player because it has profound effects on human health. And of course, the Center for Disease Control is like the gold standard for getting really fast studies done very rigorously. And they studied the consequences of the smoke in the Northeast. The results are pretty staggering. So on June 7th, which was the day that had the worst air quality in New York, we saw an 82% increase over average in asthma-associated ER visits statewide. So it has very important effects on respiratory diseases. It can exacerbate COVID-19, for example. But smoke can also have a myriad other effects on human health, including potentially complications with pregnancy, and of course, exacerbating or increasing the risk of a variety of cancers. And these health effects were even were able to be seen in the data nationally. So across the 19 days of the highest smoke impacts nationally, the CDC quantified that there was a 17% increase over average in hospital visits. So, pretty profound impacts on people. Now, the question that often accompanies this is, well, is this a one-off? We haven't experienced a lot of smoke in the Northeast. Was this a weird thing? And of course, from a historical perspective, it was pretty much an extraordinary event. But given the trends that climate change are going, as we're going to spend some time talking about today, it's almost certain that these historically extraordinary events are going to become a new normal. And so I would say with pretty clear confidence that smoke is going to be an increasing part of our lives here, even in the Northeast, where we're largely isolated from much of the North American crisis. So before we go into the details of how climate change is driving these increases in fire, I wanted to just spend a little bit of time of backing off and thinking through, well, what are the ingredients that are needed for fire? And then how does that relate to the tools that we have for managing fire? Because I think that'll give us a nice foundation for then thinking about how fire regimes are changing. When it boils down to it, fire is actually quite a simple physical process. Um, you can represent it in terms of a triangle. So at the base or the foundation, we have to have fuels to start a fire, right? And the variables that matter for that are the amount of fuels, how those fuels are arranged across the landscape. Are they really connected? Or are they really spread apart? And then the moisture content of those fuels. So how dry are they, right? Like for anybody that has a wood stove, of course, you don't throw wet wood into the fire. You'll let it dry out for a couple of years before you use it. That's where it ties in with weather, another important part of the triangle. And here, temperature, humidity, and precipitation are really important determinants of that fuel moisture content. The other factor that matters a lot is wind. So wind is one of the major factors that determines how fast fires can spread through a landscape. And then the final factor that matters is topography, particularly slope and aspect. So think about, two landscapes, one that's really smooth and well connected. A fire is going to be able to move for that much easier than another landscape that has a big mountain range with cliffs with no trees or ice at the top. That makes it much more difficult for a fire to spread. Now, the tools that we have for managing fire tie directly to this triangle, which is why it's a nice foundation. At the really broad scale, mitigating climate change and adaptation to climate change can help us ameliorate the effects of anthropogenic emissions on weather and climate, so ameliorating drought. But even at the local scale, this triangle matters a lot because the tools we have at local scales, like mechanical thinning, prescribed burning, and wildland fire use, are all about manipulating the amount and the arrangement of fuels. So prescribed burning is kind of the gold standard, and this is actually igniting fires when conditions are safe and risk is low to consume some of those surface fuels, which reduces the risk of high severity catastrophic fire later. Mechanical thinning is meant to try to replicate the effects of prescribed burning, but without the risk of having to light any fire at all. So that's going out and thinning the forest to reduce those fuel loads. Then another really interesting tool that we have that's increasingly being used is called wildland fire use. This is actually allowing wildfires to burn. So these are naturally caused fires to burn when conditions are safe or risk is low so that it can consume those fuels, which would reduce the risk of subsequent fire. And then as a last case scenario, when risk is high, people are threatened, then of course we need to use suppression to try to fight those fires. So we're looking at a picture here from Eastern Washington. It's really, really cool. This was a landscape scale experiment that State Forestry started, I think it's almost 2 decades ago, where they started regularly prescribed burning and mechanically thinning this hillside to try to get the forest structure back to what it looked like before Euro-American settlement. You'll notice the trees are really spread out in that kind of park-like look. And they burn this every 1 to 5 years, consuming those surface fuels. So it's kind of a wonderful example or test case of what forests might have looked like before Euro-American settlement, and potentially more resilient to fires than the forests we have today. Now, another question I get all the time is, well, mechanical thinning sounds a heck of a lot like logging. What's the difference? And this is a super important distinction. It turns out that when you are thinning mechanically, you're not going for the big diameter stuff that you're going to take to the mill, right? You're actually removing the really small diameter and understory vegetation, because these are the fine and flashy fuels that dry out quickest and then carry fire really quickly. So when I talk to kids, I often say like, oh, hey, when you have a campfire and you really want it to flare up and get some heat going, do you throw on a big log? Or do you throw on some dried flashy needles? And of course, even children understand that you throw on needles to get the fire to flare up. And the same thing is true with wildfires. It's those flashy fuels that are carrying fire, and that's what mechanical thinning is trying to target. So here we're looking at a picture from southwestern Colorado where a forester is removing some understory gamble oak in a really productive, beautiful ponderosa pine forest. You can see the big trees in the background. And by reducing those fine fuels, that fire can now move through this forest understory without ever affecting the mature trees at all, because it can't get up into the canopy, which would actually cause damage to those mature trees. So the fourth question that I often get asked is, how has fire changed in the Western United States over the past few decades? You know, if you just trusted the New York Times, it might seem like an apocalypse. So what does the data actually tell us? Well, it's not far off from the profound changes that the media suggests. We've seen quite rampant climate change in Western North America in particular. So, as we're going to talk about in a little bit, as the climate is warming, it's drying out our fuels at a very rapid rate. This is increasing the dryness at the height of the fire season, but it's also extending the length of the fire season. So across the Rocky Mountains and a lot of forests of the West, there would be snowpack well into June, right? And you can't have fire if your forests are buried under a meter of snow. But as we start to warm conditions, that snow is melting out earlier and earlier, sometimes April, early May. And that means that vegetation is now vulnerable to fire. So we're getting more fires during the height of the season, and the season is lengthening. And that has led to a 1,320% increase in the annual forest area burned from today since 1984. Now, 1984 is kind of a weird year, but that is the year in which satellites came online that allowed us to start tracking fires. So that's the first year where we have solid observations of where burned. Now, a 1,300% increase is shocking, and it's exemplified by a couple record-breaking years. So I wanted to point out 2020, which is the year that is the record so far, followed closely behind by 2021. And we're going to use those as benchmarks for when we think about future activity in subsequent parts of this talk. Now, the other thing that's making it that's contributing to the increases in fire and the risk from those fires is people. So it turns out that people start across the United States 85% of fires. And those ignitions are most likely to occur in what we call the wildland-urban interface, which is just a ridiculously fancy scientific term for areas where houses are near or abutting wild vegetation. So, that's the houses interspersed with forest. And out west, that's where the fire risk, of course, is highest. So people start a lot of fires there, and that wildland-urban interface is expanding very rapidly. So a collaborator of mine who studies this has shown that by 1990, there was roughly 10 million homes in the wildland-urban interface of the West, and by 2020, that's increased to 16.1 million. So that's, a lot more people out there starting fires and a lot more people and structures that are at risk from the fires that start. So what are the environmental justice implications of having all these fires burning and having the wildland-urban interface expand? If you'd asked me as a kid, my kind of vision of what the wildland-urban interface looked like would be closer to this in Jackson Hole, right? It was all the rich people who wanted to live out in the beautiful forest, enjoy the natural amenities. They'd build their mansion out there. But increasingly, that's not always the case. And in particular, like in places like California, Western Washington, Western Oregon, what we're now seeing emerge more and more in these places is that the high cost of living in urban centers is forcing poor people out into the wildland-urban interface because they can't afford to live in the city. And so now some of the most socially vulnerable folks are the ones that are at the highest risk of fire in these more populated Western states. And of course, if a fire burns through this trailer park in California, that's going to have profoundly different consequences for those folks as compared to whoever owns this mansion here in Jackson Hole. And I hope it's none of you. I just pulled it off the internet. The financial capital, the social capital is profoundly different. And so there's really complex implications for society and communities. One of the main examples that of this situation in California, of course, is Paradise, California, which was an entire town that was quite rural and relatively impoverished, that was completely consumed. And I went online trying to find pictures of before and after in Paradise. Couldn't find a single picture of what Paradise looked before. It's only pictures of what it looked like afterwards. So what is the difference between healthy good fire and catastrophic bad fire? I've kind of talked about it here, pretty loosely. Sometimes it's good, it's a fundamental Earth system process. Other times it's catastrophic and bad. Scientists also ask me this question all the time. So I think it's really important to try to be very clear about that. It turns out that good fire is all about what the system can handle and what the system is adapted to, right? So if these forests have been burning for thousands of years, the tree species are evolutionarily adapted to the frequencies of fires, the sizes of fires, the severities of fires that they experienced for thousands of years. And that varies a lot across the Western United States. So in the Southwestern United States, fires would burn before Euro-American settlement every 1 to 5 years. They were low severity. And the forest species, the southern ponderosa pine, the pinon pine, are all adapted to that fire regime. Now in Yellowstone National Park, it's fundamentally different. These forests have always burned as high severity stand replacing fires where those mature trees were killed. And the dominant tree species, lodgepole pine, is also adapted to that. So they produce these serotinous cones, which just means it's a cone that stays closed because it's got a lot of resin in it for many years until that resin is heated by fire, dries it out, it allows the cone to open, and that cone then drops seeds into the post-fire environment. Now, historically, that post-fire environment had a lot of light. There was a flush of nutrients from the combustion of all the biomass there. And even sometimes you'd see an increase in water because there wasn't as much water uptake by the mature forest. And that was prime conditions for tree seedlings to establish. Now, Yellowstone is kind of the epicenter of what I've been referring to as the large fire era. In 1988, there was a series of massive wildfires through Yellowstone. And those are said to have ushered in this period. It was kind of unprecedented, at least in lived experience. It took everybody by surprise. So the media looked at these landscapes that had been burned and called them moonscapes. There was headlines like Yellowstone National Park was ruined. But it turns out that simply wasn't the case. My PhD advisor has worked there for 35 years now and has tracked the recovery from these 88 fires. I did my PhD in these forests as well. And you can see from this lookout point here how those forests recovered to dominant lodgepole pine that are structurally and functionally very similar to what was there before the fire. So, if you go to Yellowstone today, you probably wouldn't even know that the 88 fires had happened. You wouldn't see it on the landscape, really. But why are the fires today different, and how are they reshaping ecosystems? So what's changing? Well, it turns out a lot is changing. And the big player is climate change. Conditions are drying at just extraordinary rates in the Western United States. And it all ties in with temperature. So as the atmosphere warms, it physically is just capable of holding more moisture in the atmosphere. And that moisture has to come from somewhere. And so like a straw sucking out a Coca-Cola, the atmosphere is pulling moisture from our land surface and the fuels, and then keeping it up in the atmosphere, which dries those fuels out. Some work that my collaborators did using tree rings to quantify this has demonstrated that we just emerged from the driest 2-decade period in 1,200 years in Western North America. So the drying we're already experiencing today is nearly unprecedented, and the conditions are only suggesting that it will continue to dry. And it turns out as you dry those forests out, that really changes the fire regime. So as fires become a lot more frequent compared to what forests were used to, as they become a much larger and as they become more severe, that's when you can really start to see ecosystem change. Because if they're burning really frequently, then the trees that were there before the second fire may not have cones to be able to support tree regeneration. Or if the patches are really, really large, then you might not get seed blown in from the unburned edges. And in this case, even if you have mature forest on site, if it's super hot and dry afterwards, those tree seedlings are just going to get scorched and killed off. So this is a fire that burned about 10 years ago at low elevation tree line in eastern Washington. We visited this site this summer. A collaborator has been sampling it for the entire 10 years since it's burned. And as you walk through here, and of course they do it systematically, there is not a tree seedling to be found, despite the fact that there's plenty of mature forest right on the edges to provide seeds. And the reason is because it's simply too hot and dry now for seedlings to establish. So this portion of this landscape is almost certainly going to remain grassland and shrubland for decades to centuries to come. And it turns out that, this is not a one-off situation in eastern Washington. This is a widespread phenomenon across western US forests. So a recent study just quantified that if 20% of forests in the Sierra Nevada of California were to burn today, this would be the most likely outcome. The conditions are now too dry and hot for seedlings to be able to establish anymore. 20% of the Sierras is a huge land area. It's crazy. But of course, climate change isn't the only player in town, right? People have suppressed fires. So how does that contribute? Well, for thousands of years, it turns out that people have still been starting fires in western US forests. Indigenous communities have used fire quite extensively in the western US for thousands of years. Cultural burns, they did this to create, for very intentional reasons, to create wildlife habitat that made it easier to hunt, to improve the provision of wild foods like berries and acorns from oaks that they ground into flour. But when Euro-American settlers started arriving, they extirpated cultural burning almost immediately. In California, it was actually banned by state law in 1850. And then shortly following that, right in 1910, this is at the very beginning of the US Forest Service, the big burn happened in Idaho, Montana, and Wyoming. 80 people were killed. It burned an area the size of Connecticut, and it just totally took the Forest Service by surprise. They'd never seen anything like it. And so that, at that very infant point of the Forest Service life, had profound effects on how they approached managing forests and fire for the next century. And the policy was basically universal fire suppression. This was formalized in 1935 with the 10 a.m. policy, which decreed that every fire should be suppressed by 10 a.m. the next day following its initial report. And of course, very effective marketing, Smokey the Bear has played an important role in getting that message out. What this did is it led to a densification of our forests in many places that for thousands of years had been experiencing very frequent fire and needed that fire. So you got increased fuel loads and increased connectivity of those fuel loads that now, in combination with climate change, makes fires much more catastrophic and high in severity. California is a wonderful case study for this. So in the 1800s, right before that state law was passed in 1850, it's been estimated that roughly 1.5 million acres of forest burned each year. And by 1950 to 1999, that had been reduced to 57,000 acres per year. So we were quite effective at suppressing fire through the 1900s. And you can see just by looking at historical images how that changed fuel loads. So here we're looking at pictures of Yosemite Valley at the end of in 1899. And then pictures in 2011 of that exact same location. Look how much more fuel there is, how it's much more connected. And think about a wildfire moving through these two different the same landscape at two different time periods. And think about what the consequences might be. So where is Western US fire likely to go from here? Well, conditions are expected to continue to warm and dry, and that is almost certain to cause massive increases in burned area. Models predict that by 2100, the risk of extreme drought is expected to increase by 300% as compared to what we're experiencing today in the Western United States, which was already the driest period in 1200 years. So the landscapes are just going to become profoundly more dry. And that is likely to continue to increase burning, at least for the next few decades. So I spend a lot of my day building computer models that we can then use to simulate forests and fire out through 2100 with these future climate scenarios. And what we're looking at here in this time series is results from those simulations. The yellow is just a bunch of different simulations. We run the model like 500 times, and because fire is stochastic or there's random elements to it, we get kind of different outcomes each year. But that envelope gives us an understanding of what the plausible future in any given year might look like. The orange shows what the mean of that ensemble of simulations is. And then I put in pink how much area burned in 2020, which is our current record, right? So this was that unprecedented year that I asked you to keep in mind as a benchmark. Note that 2020 becomes the average by 2050 in terms of area burned. And there are years in our simulations where 10% of all Western forest area burns. Massive increases. Now, this is where that scientific uncertainty comes in, because if you burn through all your fuels, how can you have fire even if climate change continues to ramp up? And so there is a lot of uncertainty about where we're going to lose forests, where we're going to see fuels reduce so much that it can no longer carry fire, and when. So we've talked a lot about fire in the West. What about fire in the Northeast? You know, for most of us, that smoke event this summer was kind of our main lived experience with fire. But this landscape, you know, experienced fire as well. And there's a couple examples of that I dug out that were kind of interesting. So both in 1903 and in 1908, there was big fires in the Adirondacks. These were started by people. I think they were started by sparks coming off of railroads. They burned at high severity, killed a bunch of trees. So fire is, you know, it's something that these northeastern landscapes have certainly experienced, and the fire observation towers that we see all over the landscape today are exemplary of that. But that policy of suppression that started right around 1910 in the United States has had really different effects here than it's had in Western forests, and in kind of wild ways. So what we're looking at here is a map that synthesizes information from a bunch of different sources of what the fire regimes looked like in the East before Euro-American settlement, and then what it looks like today. And the warmer colors mean fire was more frequent. The bluer colors mean it was rare. So you can see that we've shifted from more frequent fire to less frequent fire with fire suppression in eastern forests. And the reason for that is, unlike in the West, where what we saw was a densification of fuels, the same tree species growing in the East, we've actually seen transitions in forest type away from more widespread oak woodlands to wetter, moist, temperate deciduous forest, which is less fire prone. But they term this the mesification of eastern forests. So it's this really interesting feedback that actually by suppressing fire, we're reducing fire in these landscapes. Very different from the West. But it's also, I think, really important to remember that small fires can destroy structures just fine, threaten people. And a kind of a really important case study of that was in Colorado. It's the 2021 Marshall Fire. So this fire, it ignited right at the foothills of the Front Range in Colorado and Boulder County, blew through with high winds through grasslands, and it turns out it was, it was really small. It was almost so small that our satellite records wouldn't have even recorded it. So we wouldn't have even known it had happened. But because of where it happened in that wildland urban interface, more than 1,000 homes were lost, a couple people died, and it caused $2 billion in damage, right? So some of the small fires are the most destructive. And one thing that I can't help but think about is just how much wildland urban interface we have in the Northeast, right? So this is a map produced by a colleague that just quantified how much land area is within the wildland urban interface in 2020. And some of the states that we think about where homes are we think of them as being most at risk, like California, for example, only 6.6% of the land area is WUI. Colorado, which we just talked about, 4%. New York, where I'm currently residing, has 27% of its land area in wildland urban interface. And Connecticut has 42%, right? So we have a ton of homes interspersed amongst forested vegetation. Now that vegetation is pretty wet, and climate change is expected to be modest here compared to the West, of course. But we do have small fires. It is plausible that modest landscape drying could happen over the next century. And that suggests that fire could start to play a modestly more prevalent role. Now, it seems to me pretty straightforward to learn lessons from the experiences that we're having out west so that we're prepared here, both at a local, state, and regional level, to deal with any increases in fire that we have to ameliorate that risk. And it's really fun. There's a group of scientists, kind of grassroots, that have just been coming together. I've been going around telling the Western US story, and all of these scientists come up to me and say, well, what about fires in the Northeast? So we're actually getting together for a call in January to start to think about what are some of the research questions that we might want to address here that we think are really important to help us get prepared and to help us deal with this. So, I think about this every day. This is my job, is to think about fire, and sometimes it can be really depressing, despite the fact that I started out, making the case for optimism. But there are a lot of strategies that we think can work, and we think there is a future where you can live more sustainably with fire. So we really try to do solutions-oriented work to address it. And there's a couple things that I think are really important that can be done. The first thing that we have to do as a society is accept the benefits of fire in our landscapes. We have to get out of the suppression mindset, because these are the tools that reduce fuels are critical for reducing the risk of catastrophic climate change driven fire when it comes into these systems. That means we need to get more acres burned in prescribed fire, and we need to expand operations for mechanical thinning. Now, there's some challenges with both of these, right? So with prescribed fire, they don't produce as much smoke, but they still produce smoke, and people hate breathing in smoke for good reason. And so that can be a real challenge. And part of it is education to say, yes, it's annoying, but the health effects are really different from prescribed fire smoke as they are from catastrophic wildfire smoke. We're used to wearing masks after 3 years of a hellacious pandemic, so let's continue to do that. Another challenge is, despite the fact that the Forest Service has unbelievable experts in how to do prescribed burns safely, less than 1% sometimes escape. And those escape fires can have real damaging effects. So we have to figure out how to minimize those effects and also do education about, the costs and benefits of those escape fires. With mechanical thinning, because we're removing the small diameter stuff, there's real economic challenges that we face, because you can't take that stuff to mill, right? It's not economically valuable. So, Congress has allocated a bunch of money, but nobody wants to take the contracts to go do this stuff. And so we need innovation in how we use that small diameter material. And actually, there's some really amazing progress being made. So with another project, I work with folks at the University of Idaho, and there's an engineer there who has developed technology to take the small diameter materials, to grind it up, to mix it with adhesive and some fire retardant chemicals, and he is 3D printing houses with it that are flame resistant and very economical. So there's a lot of really cool kind of technology that is right in its infancy that might change the game economically. Then the other thing we really need to think about is how to address those profound scientific uncertainties that I started mentioning at the beginning of the talk. And this is mainly where we've been working. So I've been launching a new very large project called the Western Fire and Forest Resilience Collaborative that's been really generously seed funded by the Gordon and Betty Moore Foundation and now Lyda Hills Philanthropy. And our goal is to engage a bunch of, some of the US's best fire ecologists and forest scientists to think about how we can co-create a research program that helps us advance the predictive science of fire ecology and forest resilience to support decision makers during this time of profound uncertainty. It's one thing to be a scientist studying this. It's another thing to be in the Forest Service, actually having to make real decisions about how to steward our ecosystems facing this profound change. And so we're really trying to work with stakeholders in state and federal government, in the nonprofit sector, to figure out what kind of science can be done to help them in their jobs. And we have 5 pretty ambitious objectives that we're going to be working on over the next 5 to 10 years, depending on how long we can keep funding going for it. So the first is we really need to understand the mechanisms that are underpinning why forests are resilient to historical fires and why they're no longer remaining resilient. So why are trees not coming back after fires today? And to do this, we're setting up both fieldwork and large-scale experiments across many of the forests of the Western United States to really try to identify what are the factors that are most constraining tree seedling establishment. This is really important from a basic science perspective, but it also has really important application because foresters go out and reseed and plant seedlings all the time after fires in the West. And if you can give them very direct, relevant information about when and where to plant those seeds and seedlings, that can improve their success at getting those to root. That information is then being used in combination with satellites that are orbiting Earth and some machine learning and artificial intelligence to be able to then track how our forests and fire regimes are changing today in almost real time across the West. And this is critically important for tracking our baseline, so understanding our current conditions of forest and fire. And then we use that information to initialize simulation models. So basically representing forests and fire in computers, which allows us to then simulate out essentially what our forests and fire regimes might look like, both with climate change, but also by testing the different management strategies at different scales that are going out on the landscape. And then we can use that to quantify the consequences for the ecosystem services that people rely on. So of course, air quality, we can track where smoke moves from these fires across the Western United States and what the health consequences are. We can track carbon storage, which is critically important as a natural climate solution to mitigate climate change. And then even understanding the effects of fire and changes in forests on the provisioning of water. The Western US is super arid. It's already drying and it's going to continue to dry. So for example, Phoenix is already starting to limit development because they're running out of groundwater. And so understanding how much water there's going to be and what quality that water is going to be is critically important. And none of this is going to matter at all if we just dump it in the ivory tower and nobody reads it. And so we're really trying to do this in a community of practice with decision makers as partners in the research so that our science is responsive to what their needs are and how those needs evolve over the next decade. And also so that the science can be immediately ejected into that decision making because we've already built relationships of trust with folks. So one of the really fun things about starting this project is you get to pick your team, right? And it's been just a blast to go out and try to find the absolute rock stars of fire ecology and forest science. And I think we've done pretty well. So Park Williams, who's at University of California, Los Angeles, was just awarded by the MacArthur Foundation one of their Genius Fellowships. So we have a literal genius on the project, and I give him no end of grief about that. He hates it. And then Volker Radloff was just in the New York Times for that wildland urban interface stuff. So we got a bunch of really smart, passionate people working on this problem. And we have, you know, despite the profound gravity of the situation, we have a lot of fun and we really enjoy each other. So I always want to end with what can you do? And there's a bunch of stuff that we even as individuals can do. So the first is that, as I mentioned, we really need to get people to change their mindset about beneficial fire, to support beneficial fire, to advocate for it. And so to the extent that you can support prescribed fire where it's ecologically appropriate, that would really go a long ways, whether it's talking to your friends, you know, out west or even around here, talking to policymakers that you interact with, that's really valuable. The other thing is that we really need to continue to and expand the funding for science on this topic. Turns out that fire science is something that kind of falls through the cracks. So it's too applied for the National Science Foundation to really want to touch it. And then the organizations that the federal government has set up for it, namely this program called Joint Fire Science Program, is constantly on the chopping block. Congress constantly wants to cut it for whatever reason. And so we're battling tooth and nail to just get funds to do this work. So whatever you can do to fund fire science, that's really valuable, including, you know, getting out your checkbook if you have the means to do it, or talking to your policymakers and telling them how important it is to fund this stuff. And then the final thing is climate mitigation is the, you know, 100,000-pound gorilla in the room. The silver bullet solution to addressing the fire crisis is to ameliorate climate change. We need national and international policies for reducing emissions radically and upping adaptation. And so I would suggest advocating to your policymakers for meaningful legislation that makes progress towards that. So that's all I got for you. I'd be happy to take any questions. Thanks for coming out. This has been fun.
All right. All right, thank you, Winslow. That was very informative. Be happy to take any questions if anyone has any here in person.
Am I allowed
If
to
not-
ask one? Oh,
Oh,
go ahead,
there's one.
Star.
Go ahead.
Is that based on your modeling projections for the coming, say, century, Winslow, it would appear that we're rapidly rolling into sort of what they call a positive feedback loops, where forests, if forests are a natural climate solution, as your last slide sort of suggested, and the importance of it, we're at the same time going to lose a lot of that carbon sequestration capability, it would appear, and that where those two meet, wouldn't that be the obvious? I mean, it seems to be an obvious place to drive the science and the policy together, I would guess. I mean, don't you think there's a positive feedback loop kicking in here?
Absolutely. Yeah. And that's one of the reasons, you know, like for any of you who have interacted with Charlie Canham, he would start talking for 2 hours about this. But it's a passionate subject. But the thing that we have to realize, so there's all this like greenwashing and like you know, like hoorah rah about forests saving us from climate change. And in many ways, it can help and it is an important component. But for all of the projects where we, you know, add forests to the landscape or reforest places, if we lose forests in another place because of fire, it doesn't matter. And so this focus on afforestation and reforestation is really problematic. I think about it like a bank account, right? So if you're putting $1 into your bank account, but the banker's taking $3 out the back in fees, you're losing money. And fire not just in Western United States, but especially in the boreal biome, which burns like crazy, is consuming carbon at unprecedented and like hard to imagine amounts. And so if we don't think about how to manage the current fire situation, afforestation and reforestation in the tropics is spitting out in the ocean.
Thank you.
Good, Jim.
Very interesting talk. You talked at the beginning about the increase of wildfire in Canada. You didn't talk too much during your talk. Do they have similar projects going on up there for increasing prescribed fire and things like that?
Yeah, it's a really interesting system that has a lot of similarities to the Western US and some differences. So kind of similar to Yellowstone, those forests have always burned in very high severity stand replacing fires for, thousands to millions of years. And the fuel loads are pretty different. So it's really driven by the buildup of moss in the surface layer rather than the trees themselves. And so prescribed fire is something that people are exploring, but it's not likely to have nearly as much of an effective impact as, say, forests in the Southwest, where they burned every 1 to 5 years. And it's those surface fuels, the small trees that are driving increases in fire. So because those systems are different, prescribed fire may not have as much of an impact, but people are certainly experimenting with it and exploring what kind of impacts it can have.
I have a question.
Good.
What is the impact on the wildlife?
Question on what's the impact on the wildlife?
Yeah, really great question. It's really complicated. So there are some species that really depend on old growth forest, spotted owl being, the classic, iconic, most controversial one. There are other species that really jam on early post-fire forests. So there's this bird called the black-backed woodpecker that if you look at it, it is literally camouflaged to hide on standing black snags. And they use post-fire environments extensively. And then there are some species that we thought would care a lot and they just don't care at all. So elk, for example, in Yellowstone, move through unburned, burned forest just fine. Even when there's big snags built up on the ground, they can move through it, no problem. So there's a whole, like all these different species use it in really different ways. And some of them are gonna, be severely impacted in negative ways by the loss of old growth forests with increasing fires. Others are gonna benefit, and then some we just don't know.
I think we have a few questions from our virtual audience.
A question about who you might be trying to target for policy decision-making. And is there any level that you wouldn't tackle, but how do you prioritize who needs the education and suggestions on, making the right decisions?
Yeah, that's a great question. And one about a year ago, we spent 2 months kind of grappling with as we were starting this project. So the first thing I would say is, it's not about education in the sense of like going into a classroom and teaching people. These people are experts in their they spend every day out in the forest. They're world's experts, more so than I am. It's about trying to figure out where the uncertainty is that nobody has any idea, and in partnership, figuring those out together. So given the domain of the projects, the whole Western United States and the modeling tools that we have and the remote sensing tools that we have, we decided that our core audience would be the regional Forest Service district person or the state person that's thinking about, policies at the California level. And then from there, once we build those relationships, we would work up to the national level and getting building relationships with folks in DC, and then starting to trickle down to the more local level. So the work we do, it's hard to be able to tell a local forester who has a couple hundred acres of forest that they're managing what to do with our models. But the person who's thinking about forest policy across California, our models are really well designed to help have impact with that. And so we've worked a lot with groups so far, like the Nature Conservancy, the Environmental Defense Fund, folks in California Natural Resources Agency, folks with Washington Department of Environmental Conservation, and folks in the Forest Service that are like at the, the regional level.
Questions from the,
That was it from, our fairly substantial remote audience.
we have another question?
Yeah, my question is about, it's been wet here in the east. And I read an article which I can't find anymore, and if you know about it, let me know, which has said that it's gonna be wet for another decade. This was a science article. But what, makes me think, well, if it could be wet for a decade here, it could also be dry. And we think of wildfires not here, and what would we do on a 10-year basis, starting now, here, in advance of a dry cycle, to fire break areas in our forests? Does anyone work on that, or it's like, oh, no, it's wet, who cares?
Yeah, it's one of these places actually where Charlie Canham and I disagree. So I bring this up all the time with Charlie, and he says, these are asbestos forests, they're never gonna burn. And I'm like, well, maybe that's the case, or maybe not, depending on how it goes. So, like there was fires in moist forests of Tennessee that burned a bunch of homes a few years ago. And actually, in preparation for this talk, I was looking at this paper that's kind of shown the migration of fire from the southeast further and further and further north. And of course, we're not here yet, but it's moving up. So there's really basic, simple things that somebody at even the local homeowner level could do in anticipation of that dry year. The main thing is reducing fuel loads around your house, right? So it is extraordinarily effective to create a 100-meter buffer around your home where you don't have trees that are touching your home, the fuels are not connected. That makes a world of difference for two reasons. First, the fire isn't going to come up next to your home in the same way. And second, it makes it really easy for firefighters to get in and do their job. So a large part of protecting homes is creating safe conditions for firefighters to fight fires, and reducing those fuel loads plays a critical role in that. So, for relatively inexpensive, you can reduce those fuel loads around your home.
Cool.
All right, I think that's all we have for questions. I'd like to thank Dr. Hansen once again for, taking the time to talk with us today. If you want more information on his work, you can visit the website of the Carey Institute, or I believe at the, your collaborative has your own website there as well.
We do, yeah, westernfireforest.org.
And I was remiss in not thanking Molly Ackerley and Mike Sconyers for underwriting the winter lecture series, of which this is the first. So thanks to them.
That's very good.
Thank you.
All right, yeah, we look forward to coming up the upcoming spring to hopefully we can have Winslow out to the forest.
That'd be
Show them
great.
around and give them a tour of Great Mountain Forest. With that, let's have another round of applause for Dr. Hansen.
Thanks so much. It's been really fun. Enjoyed chatting with you.
Thank you.
All right, thank you.
Thanks. Take care.
Stay safe.
Be careful getting cold.
What a